Thank you. All right, good morning. Um, let's do lecture 3. So where are we? I had this plan, YCFTs, which we have answered which I have tried to answer as well as I know the answer to that question, which is, as we discussed, it's not been, I don't think I have a completely satisfactory answer, and perhaps nobody has. And now we are discussing CFT axioms. And what I want to get to is a set of equations known as crossing symmetry equations. But we're going to analyze these equations in the remaining lectures. And so even though many of you perhaps have seen or heard these equations, I'm going to need them in some amount of detail. So I'm going to just also discuss some details of conformal blocks and the things that appear here. So this is still sort of, we have a fairly long road to walk to get there. And in particular to get to the details of conformal blocks. So this is kind of the target for today. And then, as I said, I want to discuss some analytic results and some numerical results later in later lectures. So I think we'll get to about here somewhere. Maybe we'll have time to discuss one or two analytic results. So, okay, I want to say some philosophical words, but I can also postpone the philosophy until we actually have equations that I can point at. So let's then do more technical stuff. So we were looking at correlation functions of the local operators, the scaling operators in a conformal field theory, and we said that one-point functions are 0 unless O is the identity operator, because the one-point function of the identity operator is 1. Two-point functions we're having this form, and let me give them an index I and j, x to the delta I plus delta j, for general scalar operators. And then if they're primaries, which I can denote by adding a little p to them, then I can choose a basis of operators such that this is delta ij. In any case, they must have exactly the same scaling dimension for this two-point function to be non-zero. Now, I have not given you is two-point functions of vector, or more generally, let me say tensor. And if you want to be general, I can say spin, anything any operator that transforms in a non-trivial representation of the rotation. And so that I have not given you, and that I will not give you. But these things exist, and you can also all the word identities for the conformal. So then, of course, you get some tensor structure. Everything messy. People have invented ways to do things, and there's a bit of an industry there, and we are not going to discuss any of that. The same actually for higher point functions. Of course, you can extend this. Everything I say, you can extend it to tensor operators. But again, I don't want to do that. So I think O3 of x3, and these are all primaries. And I gave you as an assignment to show that out of all the possible structures that I wrote yesterday, there's in fact only one structure that's compatible with scaling, rotation, and in particular this inversion. And the one structure that remains has this nice symmetric form. delta 1 plus delta 3 minus delta 2. So it's all symmetric. So I'm writing three indices, three exponents, but if you cannot read one of them, or if you read just permutation, you have three shots at trying to decipher what I'm writing. So this is in fact the 3.5 of there's only one structure with a number that is undetermined. It's undetermined in the sense that the deltas are not fixed by conformal symmetry. It's just a number that depends on the particular theory and particular operator you're looking at. Okay? And again, I mean, if you want, like, go crazy and try to deduce what the 3-point structure is for 3 spin 4 operators, and you'll find that actually there's more than one structure that you can write down, and there are a couple of numbers that you can associate to 3 spin 4 operators. But it's always a finite set if you have simple operators. So that was the homework. Let's now look at 4-point functions. And here I'll do identical operators. And they're also primary, so let me give them a little superscript. So then, of course, you have to work a little bit harder. One structure that will take care of the scaling and rotations and translations is to say, well, if I just take this 4-point function and I write a product of two 2-point functions, 1, 2, and 3, 4, that'll take care of everything because the 2-point function itself is covariant and I can just factorize this. So I'll do something like this into the prefactor, and that'll take care of scaling, of the proper scaling. So this delta is then the delta operator, and stuff like that. But then there is another function, non-trivial and not fixed. So here, remember, our function worth of freedom, U and V are. Yes? Delta is the sum of delta? Is it the sum of delta with delta? No, delta is delta of the operator. So then this is the they're all the same. It's 4 times the same operator. Again, just as doing here this for tensors, you can do this for non-identical scalars, and you have to work a bit harder. But possible, it's all written down. Most of it is written down somewhere. And again, but for simplicity, I had a few simple, and the ones that I'm going to need later, of course. So there's an arbitrary function here. Again, if you have a theory, then of course you know what if you have solved the theory, you know what this function is, but the function depends on the theory. And U and V are magical things that you can build from 4 points. So they're called conformal cross ratios. And in the typical way of writing them, they look like this. These are cross ratios. And again, because I'm to get to some technical stuff, in detail. So what is so magical about them? They're nice under translations and rotations and scaling because there's 1, 2, 3, 4, and 1, 3, 2. And furthermore, for inversion, if you remember this transformation law of x12 squared under inversion, you see that this is inversion. Because this produces, x12 squared produces a prefactor like x1 to some power and x2 to some power, and x3 some power and x4 to some power from the second term, but you get the same. Under inversion, these things are also invariant. And so since they are conformally invariant for points, I can, in principle, build an arbitrary function of them that is also conformally invariant. We will also use z variables which are defined like this. So in principle, and Euclidean points, and we're going to analytically continue them to weak rotate them to. Then if we stick in Euclidean signature, then is the complex conjugate of z star. You see, if you give me u and v, then I have two solutions to this quadratic equation. It's two quadratic equations. They're related like so, I claim. The two are related just by complex conjugation, by swapping z and z bar because it's symmetric. So one nice way to think about these z bar variables is to say there's this canonical configuration, which you may know from 2D CFT, where you put operator 1 at the origin, operator 3 at the point 1, operator 4 you send to infinity, and so in these cross ratios you send 4 to infinity, so these two guys disappear, x3 4, x2 4, and x1 4, x2 4. And then you see that if things work nicely if I put operator 2 at the point z bar in some complex plane. So this is presuming that all 4 points are in the same plane, which is something you can do with conformal transformations. And then you see what u and v are. U is just the distance between 1 and 2 in this configuration. Distance squared, because it's the modulus of z. And v, v is just the distance to operator 3 squared. So later on, operator product expansions, and we are going to push these operators towards each other. So if I want to send 1 to 2, I have to send u to 0. And if I want to send 2 to 3, I have to send v to 0. In fact, if I send 1 to 2, I send u to 0 and v becomes 1. And the other way around would be v to 0 and you sending u to 1. And in principle, you can also send operator 2 to operator 4, but it's less interesting. Okay, so these are the variables that we'll often use, these z and z bar variables. It's useful. It simplifies a lot of the equations. Any questions about this? Yeah.
Why the 4 points are coplanar?
You can do that sending an operator to. I mean, there's a little trick, right? You have your conformal symmetry, and you are allowed to move operators around. So sending 4 to infinity, I can do a translation. Send 4 to the origin, then do an inversion, and then 4 sits at infinity because it maps the origin to infinity. So I'm done with that. Then I have more translations. Well, then I have 3 operators left. 3 operators are in a plane. So then I'm good. And then on a plane, I have translations left because translations leave the point at infinity fixed. So I move operator 1 to the origin. Then in this plane, I have scaling and rotation. So I can use both of those to move operator 3 there. And then I've used up all my conformal symmetries. And 2 sits wherever it sits after this procedure. So this is always possible in any dimension, not just in 2-dimensional CFTs. Okay. So now I want to discuss the operator product expansion, or OPE, operator product expansion. But we'll have a little discussion first to make about the state operator correspondence. So let's do first a little parenthetical comment. So open parentheses, we're going to close them in a couple minutes. we had this dilatation operator, or we had these generators of the conformal algebra, but I'm in particular interested now in the dilatation operator. So D, acting on a bunch of operators, was, oh, this was actually 0, we said, and it is also just the integral of the current, the divergence of the current inside the of the divergence of the current. So this is some coordinate. Well, I also always call it y over some space m. And remember, what the important thing was really that we just picked up all the delta functions. So this can in fact be any m that sort of envelops whatever is in dot dot dot, right? So if there are two operators in dot dot dot, or let me put a bunch, then in my spacetime, then any m that envelops it will do. So any m like this will do. Of course, I can pick a different m. I can also pick a bigger m, but that's just integrating the divergence over a bigger region, which up to a boundary term doesn't really change anything. So because there are no delta function, there are no contact terms there. So one thing we can say is we can just do this integration by parts, and we say that this is the integral over the boundary of m of now with the normal derivative s mu, t mu nu y nu t mu nu of y nu dot 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 dt minus 1. And so this would be any, so I call this, let me call this S, and this would be any S surrounding whatever is in dot dot dot. So this will work, but now I can do something else. Obviously, we'll take a correlation function and we'll split stuff into two parts. This, of course, is just defined entirely analogously to this. It's just the integral of S of n mu t mu nu y nu x y, if I call them, let me give these dots names. X is a bunch of stuff and y is a bunch of other stuff. And this definition should be, this is okay for any S surrounding, well, separating x from y, right? So you can imagine what's happening if I have my spacetime, I have a bunch of stuff in x and a bunch of stuff in y. Then what I mean with this notation is that I just choose an S like this, and it'll do the job. And of course, if I take the dilatation operator and I act on everything, I get 0 because I push the stuff off to infinity. So this is also equal to minus x d on y. Okay, so people say that this is some surface operator because it's an operator defined on a hypersurface. And I can just freely deform the hypersurface because that's just, those two different hypersurfaces are just related by the integral of a divergence, and the divergence vanishes away from contact points. So as long as I don't cross any operators, I can freely deform this S. And so people call this a topological surface operator. Yes?
When we do complex generalizers, we do the same thing, but after that we deform the surface only encompass one point by reducing the surface.
Right.
Can we do the same thing here and rewrite the full operation as a sum of individual tiny surfaces around each operators?
Sure. Yeah, you can pick off an operator, right? And then you can deform the operator if you. I think it's kind of complicating your life, but in principle you can do this, and of course, operator, you know what happens. It's like crossing a pole, right? You get the delta, your contribution from the delta function. So the difference between this original S and this modified S is not zero, it's some finite term. Yeah, you can deform all that. Right, so you can, this is of course just acting with the dilatation operator on a bunch of stuff. So these x's all get scaled a bit and the y does not. And I'm saying that's the same as scaling all the y's and not the x's. All the y's up to a minus sign. Because if you scale everything, of course, then you get zero. So that's what I mean when I say I act with operator D on a bunch of x's and not on a bunch of stuff that I called x and not on something else that I called y. So close parenthesis. Okay, so now we can go back to the operator product expansion. So suppose I'm looking at the configuration like this, where let me, for concreteness, take 3 operators and then some junk. I don't know what it is, I'm going to call it psi. But think of psi as some kind of excitation that I put in the theory. One way to think of psi is to say, well, it might be like 25 local operators inserted at 20. That's what I need. Or let me say, or maybe it's some kind of complicated structure like a boundary or something odd. So there's some structure there. I'm not going to say what it is, but I'm going to make one assumption. For simplicity now, if I wrap it with the dilatation operator, then I get psi back. So psi, whatever it is some eigen gadget, eigen function, eigen state. Let's call it a state of the dilatation. Of course, there's a whole story here to be told about radial quantization that you may or may not know, but I'm going to try to be more efficient and skip all that. I think I can still get my main point across. So I look at this thing, OX2, OX3, psi, inside my correlation function. And now I'm going to insert not just here, but I'm going to exponentiate the dilatation operator. So I insert d, think of this. So d squared. About contact points, just take them in infinitesimal distance apart. It turns out that there's no problem with contact points, and you can just put them on top of each other. But it all gives the same effect, yeah.
So the delta psi is not from a weight, it's just a number.
Yeah, it's just an eigenvalue at this point, yeah. It'll be a conformal weight in a second. So what is this? Well, this is, of course, O1, O2, O3, e to the zeta times delta psi times psi. So it's the original correlation function, and the zeta dependence here completely factorizes it. But I can also just act with the dilatation operator in the other sense. So that means not just an infinitesimal rescaling, but actually a finite rescaling of the operators. Of the operators' insertion points. There's psi, and then there is the dilatation operator doesn't just fill the positions, it also inserts it also rescales the operators with their weight. I think this is a plus, it might be a minus, sorry. I'm a bit hesitant. So let me say plus minus, it doesn't matter. Right, so now just look at this correlation function here. Look at the zeta dependence. What happens if I rescale all the operators? Well, the dependence of this correlation function is just completely captured in these exponentials. There's one exponential here that factors out, and there's an exponential here. But it is completely fine, right? So these operators, I can rescale them without ever encountering a singularity. Yes? Yeah, minus, yes. All I want to get at, yes, thank you. All I want to get at is that the zeta dependence is fine. So I didn't check that all the factors right, yeah. Right, the zeta dependence is completely fine. There's nothing wrong with rescaling these operators. In particular, I can rescale these operators. This psi had some finite size, I assume that. But I can rescale these psi. Right up until zeta minus infinity, and these operators sit at the origin, and it can blow up. So that no matter what it is, if it is an eigenstate of the dilatation operator, then actually you don't hit any singularity problem. If you just scale any operators or four operators or you probe it with any operators, you can just scale them all to zero. The only point where you're ever going to see a problem is at the origin. So this blob, I want to draw the same blob, psi, is really, so let's me suppose that this point is the origin, is really just some localized excitation at the origin and nothing else. But this is a local operator, right? It's supported at a point. So this would just be a local primary. It may not have good Lorentz transformation properties, but in principle, it's just a local operator. So this is, in a nutshell, what people call the state operator correspondence. No, this is a first step towards the state operator correspondence, if I want to be precise. But it says that any psi that is an eigenfunction of dilatation operator is really just a local operator. If you say, well, it's maybe a new operator, it wasn't in my list of operators to begin with. But that's just that your list is complete. The list of all the local operators, the list of all the stuff that you get psi and shrinking it to zero. So any state will in the end, any state that's an eigenvalue of dilatation operator will shrink to a local operator. And conversely, could always have been the insertion of the origin. That would be one way to generate a psi that's an eigenfunction of dilatation. So there's also a map from operators. Now again, I say the word state without introducing radial quantization, but you can ask me in a discussion session or afterwards what these words radial quantization really mean. So now we suppose sorry, was this clear? Yeah. Suppose that D is actually diagonalizable and has discrete spectrum, which again is something that is true in any reasonable reflection positive conformal field theory. And so it's not a huge assumption to make reflection positivity. Then, of course, then I can diagonalize it. So if I have any sort of blob chi that's not an eigenfunction of the dilatation operator, then I can diagonalize it with some coefficients over the local operators, because it states that eigenfunctions of the dilatation operators are local operators. Maybe with Lorentz indices, they're descendants, maybe they're primaries, I don't care. It's just something like this should exist. And this should, if this dilatation operator is really that nicely behaved and your Hilbert space is or the spectrum is discrete, okay, maybe up to one little subtlety, but let me claim that in reasonable conformal field theory this converges. This is a convergent sum. Yeah. Has to contain the origin. Yeah. Good. Let me put it not in the middle. It doesn't matter. The origin. Sorry, this is 0. Yeah. But that's just because the dilatation operator is kind of a wacky operator because it singles out the origin. I can always compose the dilatation operator with the translation and take any point x in psi. Right? It can be any point in psi. It doesn't have to be the center of psi. Chi. Any point, this works. So let me take one example, which is the most important example, where this chi is just two operators. One operator inserted at x1, one operator at x2. Then we have, let me do. Oh, I can keep more or less the order. I should number my boards.
I'm sorry?
Yes.
C chi to the k. It's
No, sorry, it's a coefficient. Okay, thanks. Sorry. I try to adhere to summation convention, and then I still write some k, and then it's a big mess. Sorry, it doesn't always work what I do. So take that example. Then we'll have that O of x1, O of x2, any other junk, as long as, of course, the other junk doesn't come too close to x1 or x2. I get a sum over, in principle, all operators. I'm going to refine this gradually. So if you're taking notes, you have to write this line a bunch of times. And then we'll just write OK of x, well, OK, and then junk, right? We take these two operators, and I write them as a sum of local operators. Now let's clean things up a bit. So there are some coefficients that they depend on. Let me give these. These coefficients depend on x1 and x2. If I change them a little bit, the coefficients will change. So these coefficients, they will be functions of x1 and x2. And what else should I say? They depend on the operators under consideration. So they will have indices 1 to k. They will also depend, of course, on the point where I fuse together. What do I call the effective origin when I start implementing this so-called operator product expansion? Well, in practice, it's convenient. Well, a natural way to do this would be to pick the midpoint between 1 and 2, but we'll do a slightly unnatural thing, which is not really problematic. We'll just center the expansion around operator, the location of operator 2. Why not? The rest is just, I mean, it's a convergent sum. You just reshuffle terms in the sum around. Now, this operator here does not necessarily need to be a Lorentz scalar, right? It could be a Lorentz tensor in principle. If these two are scalars, you're not going to get the spinor out of two scalars. But you could get a tensor. So let me give it indices, mu1 to mu L, x2. And then these indices, they're not there, so they must appear here. And this gadget only depends on 1 and 2, so I can absorb them by x12 mu1 to x12 mu L. That'll do the job. And then, of course, I have to reinsert the coefficient. So this is what I said. I was going to rewrite it. Sum over all operators. So x12 mu1 to x12 mu L. And then we have the C12k, which depends on x1 and x2. But again, of course, this thing should be translation invariant. So this really can depend only on x1 minus x2. I just want to absorb the indices. Right, this operator now has L indices. So what am I going to do with them? My claim is that the only thing I can do with them is absorb them in x12. So by translation invariance, you can also see that this can only depend on x12, and then you have to, believe me, there's a little bit of extra work involved, which is that the scaling invariance tells you that this coefficient is really just C12k. And then scaling must come out correctly, which will be if it's delta 1 plus delta 2 minus delta k. And then there are L of these x12s at the top, so I'll also have to offset them with an extra factor. So my claim is that this is the entire x12 dependence, and the rest is just numbers. So there's a sum over all operators k in the theories, some coefficients, this particular structure. And then, and that's it. So this is the operator product expansion. So what it does is something magical for you, because you take two operators, so you take, say, a 5-point function, and you just fuse the operators together and write it as a sum of new operators. It's a 4-point function now. Do it again, it's a 3-point function. Do it again, it's a 2-point function. So all the higher correlation functions, you can just reduce them by successive applications of the operator product expansion to 2-point functions, 1-point functions. L is the spin of the operator. So these are Lorentz indices, mu, nu, rho. And so mu, nu, rho, but I have spin L in principle. And now we should go there. Okay, let's play this game. Let's apply it. So we'll just do, well, 1-point functions, there's no product to take. So a 2-point function. Is this clear? Am I mistake free when it comes to these equations? I think I did it correctly. Yeah.
But you also suppose that these they are flexible, but we know these. What can change for these?
If it's not diagonalizable,
I mean, we know that D acts as F, D, and the difference.
but I said if you act with D on a local operator, you get the same operator back up till prefactor. That doesn't have to be. You can get a linear combination back in principle. Right? This would not be nice, but this goes back to this original question. D is sort of the derivative of the beta function at the fixed point, diagonalized. Right? It's a matrix that's not symmetric that you're trying to diagonalize. But the matrix can have like all kinds of nasty things. It can have a Jordan block form. Right? It's not a symmetric matrix. This is not great.
Yeah, I'm confused because we know D.
Yeah, but I know D only abstractly, right? As the thing that you had the beta functions at the fixed point. This at G star. This are is in principle D. Like the action of the local operators.
I know that because G is the scaling operator.
Right.
And it's mu d mu.
Plus delta. So D is the vector field x mu d mu, and it acts like that, plus an extra term when it acts in the quantum theory. So it's a formal vector field, and then the quantum operator. But I'm still going to quantum operator. It acts in the theory, and it gives to every operator a particular kick. And my claim is that I can diagonalize the kicks, and then every operator just scales homogeneously. But that claim relies on the diagonalization of this matrix, which was not obvious. Yeah.
What do you mean by convergence? Because, well, operator expansion when x goes to 0 seems to divergence, so
When x is, yeah.
it's slow.
No, then it converges very well when x12 is 0.
What does it mean?
Well, it just means that if you put two operators on top of each other, you're doing a bad. Right? The 2-point function blows up as well. So this is actually an expansion in x12. We're going to get there. It converges as long as you don't come too close. You don't probe into chi, and then you're going to see that there's sitting something at operator 1. So if you have an operator 3 here, everything is fine. But if you move it all the way up until it touches operator 1, then it fails to converge. And that has to do with these coefficients, C chi, k not working anymore. So this converges as long as you probe chi outside of where you defined it. Yeah?
It's only a stupid question, but is there a physical picture behind UFT being far from chi?
Far from chi works better because it's the same as I move. But then, so and when 1 and 2 are close together, well, but to see that, well, you can organize them, right? So you organize them by delta. So forget about the L's for a minute. You organize them by deltas. So for very high delta, the coefficient is very, if x12 is small, this coefficient is very small. The leading coefficient is the low delta, and the high deltas, they contribute less and less. And that convergence gets better and better the smaller x12 is. Right. Yep.
If you have like 3, 4 operators in chi, do you converges as well?
Yeah. But it would be impractical to do it in that way because I rather do the OPE pairwise for reasons that we'll see. But yeah, 5 operators, anything. I think even if you put boundary conformal field theory in chi like a boundary, then it still works because then you basically, as long as you're not pushing it all the way to the boundary, you basically are looking at something. If you take the chi and its inverse, you're looking at the analog or the equivalent in hierarchy. That's technicalities. Yeah. 5 minutes. Oh yeah. Thanks. I have a strong chair today. Yes. So let's apply the OPE. Let's do 1-point functions. It's trivial, so let's look at 2-point functions. Okay. Delta J. So 2-point functions do this. Well, how does that work? We should have compatibility with OPE. So what happens? What can we say about the OPE for 2 identical primaries? Sorry? There's an identity operator in this. It must be there, right? Otherwise it doesn't work. So we'll just say all operators except the identity, and I'll just factor it out. It'll be delta 1. Sorry for writing delta 1, 2, but you know what I mean. Delta 1, 2 is a Kronecker delta. It's not 0. It's an operator 1. It's the same as operator 2. So this is the contribution of the identity operator. So okay, fine. Now we fix the 2-point functions. This is for primaries, of course. Let me make these operators primaries now, because then you get the delta 1, 2. Okay, that's 2-point functions. Let's do 3-point functions. How did I denote it? Okay. So the 3-point functions, primary scalars, again, why not? We know what it is. And then we have these other powers. I just wrote it down. So let's apply the OPE. Well, the identity operator will not contribute because it's the identity operator times a 1-point function, and operator 3 is not trivial. So the identity operator will not contribute, so we'll have a sum over k. And then schematically, all this tensor structure business. Then we have OK sitting at x2 and O3 sitting at x3. So which truncates the sum, right? Which operators contribute now? It's a 2-point function. Sorry? So only O3? And? If I write a P here, its descendants, right? O3 and its descendants. So this is only O3 and descendants. Right? Because if this is true for 2-point functions, then of course if I want to compute descendants, I just act with derivatives. So if I want to compute OI like descendants, I act with derivatives, but I definitely get something non-zero, because the derivative of this thing is not 0. So descendants also contribute. They have some strange structure of 2-point functions, descendants, but they definitely can contribute. And then we see something interesting, because now we have a sum over a primary and all of its buddies, all of its descendants, with some coefficient C1 to K. And we should get this 3-point function, but we know what this 3-point function is. We know the functional form of this. And the operator product expansion is like an expansion around small x12, right? So you can take this 3-point function, expand it around x12. For small x12, of course, these two terms are the same to leading order. And then you just get an expansion. And then you can sort of match them all term by term. You can determine all this 1 to k in terms of the 3-point function. So I should stop, but the magic here, which is why we're doing this particular y and over 2-point functions, well, that taught us that the identity should be there. The magic of applying the OPE to 3-point function is that it very clearly shows that the coefficients of descendants are not independent from the coefficient of the primary. So we get, for the primary, if you take the short distance expansion, you can check this fairly straightforwardly. You get, of course, everything is proportional to lambda 1, 3. And I think the way I wrote it, yeah, again, there could be tensor structures, but for scalars, you get that C12K, C123 is just lambda 123. But these coefficients are not new at all because the leading one, lambda, and if I look at the descendants, then I get C1, 2, and then a bunch of derivatives acting on 3. The coefficient for a descendant. Well, it's definitely still proportional to lambda 1, 2, 3 because the entire right-hand side is proportional. And then some objects that can depend only on the, right? It's just a matching of functions. And this function depends on deltas. So the only thing that this thing can possibly depend on is delta 1, delta 2, delta 3. And as it happens, also L3 if there's an operator with spin. I wrote it for scalars again. So this, the way I wrote it is it just picks out a scalar because I assumed that O3 was a scalar, but if O3 is a tensor, I just pick out the tensor and the same goes. So we can rewrite this OP again, and that's where the last thing I'll write before the break. We say we're just going to group them all together. So we'll just make it a sum of all the primary operators. And then we have to take into account the descendant. So then for the primary, we get lambda 1, 2k. And then we have to sum all the descendants. But the descendants are just derivatives. So here's the primary. And I think one good way to write it is to say that you just get something like a C, mu1 to mu L, which is just going to act on this with derivatives. And then it depends on x1, 2. So this is a thing that takes into account, right, if it starts C mu1 to mu L, x1, 2 d mu, starts with, well, basically a 1, or if I have spin, it's x1, 2 mu 1 to x1, 2 mu L over x1, 2 to the L. So that's like the 1. And then there are derivatives, something d mu plus something d mu plus dot, dot, dot. So it's some, no, let me keep it like this. This is some, of course there are infinitely many descendants, so you get some infinite order derivative operator. Whose coefficients can only depend on the deltas, delta 1, delta 2, delta 3, and L3. So maybe I should make that explicit. Delta 1, delta 2, delta 3, L3. And here the same thing. But there's no theory-dependent stuff in there except for the deltas. Everything is just fixed by conformal invariance. You give me a bunch, 3 deltas and a spin, then I can compute this infinite order differential operator by just comparing the OPE to the known 3-point function. Right? So this is the final form of the operator product expansion. It's a messy gadget, but it is what it is. These differential operators are not nice, they're not elegant, they're complicated beasts, and they're the source of sort of most of the mathematical complication of conformal field theory. So the punchline is then the following. Because what we see is that in the operator product expansion, there are just deltas and lambdas. So to know all the CFT endpoint correlation functions of local operators, of scaling operators, well, they can all be reduced by the OPE to just two-point functions. So you just need the spectrum, as it is called, the set of all operators and their spins, and the OPE coefficients, which are the same as the three-function coefficients. So it's possibly a set of data, but this is what suffices, and then to compute all the endpoint correlation functions, because the OPE can be used to compute 4, 5, 6, and higher point functions. So just 2 and 3 point functions. If you know all the point functions and all the 3 point functions, you've basically obtained all the information there is to know about CFTs. Okay. So let me stop here for a 10-minute break. 10 minutes, right? Yeah. Okay, resume at 10 past. Okay. So I said that to know all the CFT endpoint correlation function, you just need this for primaries, of course. Descendants are all taken into account by just taking derivatives. So that was, this is now the form of the OPE. We applied it to 2-point functions, we found this. We applied it to 3-point functions, and we found that we can just restrict to a sum over primaries and incorporate all the descendants by some complicated derivative operator. It's nasty, but in principle, this is correct. So those were the 2 and 3-point functions. So now let's look at 4-point functions. So let me put my 4 points at 0. Well, here's point 1. Here's operator 1. Here's operator 3. Operator 4 we kicked off to infinity, and operator 2. So it's here. So what do we get? Well, we apply the OPE. Let's do 1, 2. So we get the sum over k, lambda 1, 2k. Complicated differential operator, which depends on x1, 2. Delta, and of course, it still depends on all these deltas and stuff, but I'm not going to write that down. And then it's a differential operator with respect to x2, acting on O2, O3, O4. And now you can kind of see what happens, because this O2, O3, O4 is basically fixed up until one coefficient, right? And this is also fixed. It's fixed in terms of the delta. So you can just write that this is sum over k, lambda 1, 2k. Sorry, this is not O2, this is OK now. Inserted at x2. Let me make that a bit more clean. OK at x2, and O3 and O4 have not moved. So this is just a 3-point function, and so one way to write it is just to say, well, this is lambda 3, 4k times, and then we have some known differential operator acting on some known factor, x12 to some power, x13 to some, well, x23, x24, and x34 to some power. And for, you have to believe me that if k was a tensor operator, there would also only be one structure that would look a little bit like this. And so all this is known in the sense that it's just a function of all the positions and the quantum numbers involved, so the deltas and the spins involved, and nothing else. So this is something computed for any conformal field theory without solving the conformal field theory. It's just, as we say, a kinematically determined object. So let me summarize this by saying that this is, we'll just capture it, we'll just give it a name, or at least a letter now. So it should be a G. What does it depend on? It depends on, well, delta 1, delta 2 for sure through this C, and then delta 3, delta 4 here, and it depends on delta K and on the spin of K. So delta 1, delta 2, delta 3, delta 4, delta K, and the spin of K. And then, of course, it also depends on all the 4 positions. So x1 to x4. But it is computable. You can try to compute this, and I'll give you some explicit expressions later on. So this is what we call a conformal block. And this decomposition then of the 4-point function more precisely, it is a conformal block decomposition. Right? Does this make sense? It's just a practical implementation of this statement for 4-point functions. You give me a bunch of deltas and a bunch of lambdas, I'll just plug them into this formula, and I give you the 4-point function. Yes?
What you've done here, you choose a particular order to do the fusion.
Right?
So 1 with 2, 3 with 4, and then to join the K.
Yeah.
But could you have not taken any other route? For example, 1 with 2, the K with the 3, for example.
1 with 2, k with 3 is going to give you the same thing, because that's just applying the OPE in the 3-point function, but that just gives you the 3-point function, because that we knew already. So k with 3 or k with 4, it doesn't matter, right? You can do 3 with 4 or k with, I mean, you know this 3-point function already, but if you want to apply the OPE again, be my guest. But I know the answer, right? So.
But I think if you can do it in every direction, you still get the same expression.
Yeah, sure, it must be, yeah.
So why did you say A conformal? Is it not unique?
Well, I chose this, right? This works well if I send 1 to 2. Because that's when the P between 1 and 2 converges. But why not 1 with, well, 2 with 3, right? That's another. So I could also have fused 2 with 3. It works well if 2 is close to 3. But in fact, I mean, this OPE, this conformal block decomposition you can show converges in a big domain. I call it DS because this is also known as the S-channel conformal block decomposition. And DS, well, in this configuration is, let me see if I can draw it without messing up the plot. This is DS. It's everything except when you put exactly between 3 and 4. So it's a huge domain of conversion, except this set. And the reason is that I can always go back to this idea of encapsulating 1 and 2 into some kind of blob that I called, or some kind of circle. The game that I can do with using conformal invariance is to just draw a circle around 1 and 2, and if it doesn't touch 3 and 4, it's not an entirely trivial claim. It follows from playing a bit with conformal transformations in the plane, but that's the idea. A circle around 1 and 2, then the circle has a midpoint, and around that midpoint I can expand the OPE, and then it converges. So you see, if I put 2 close to 3, like here, I have to draw a huge circle, but I still can draw a circle. And so I still have a convergent conformal block decomposition. So that's qualitatively why it converges. You have to, I'm not sure this argument should have convinced you, but this is, with some bells and whistles, the crux of the argument as to why the conformal block decomposition converges. So the S is enormous. It definitely includes a part where 2,3 OPE also converges. So let me write down the other one, or an other one. It's also some, I mean, it's kind of the same operators, right? Because it's just all the primary operators. I'm just going to give it a different label. So let me, what did I want to do? Let me swap 1 and 3 here. That's one way to implement this. So 2, 3K, lambda 1, 4K, G delta 3, delta 2, delta 1, delta 4, delta P, delta P, LP, X3, X2. So this is the other conformal block decomposition. Just swapping, oops, sorry. Just swapping operator 1 and 3. You see, I've fused 2, 3 together and then, and 1, 4 together. And I get this conformal block. This is another one, and it converges in another huge domain, dt, which is just everything except when operator 2 sits exactly between 1 and 4, which is here, so it's dt. It does not converge when 2 is on the negative real axis. 1, 2, yeah. 4 is 4. Yeah. So I just swapped 1 and 3. So this is another conformal block decomposition. So the magic of this is, of course, that these are two decompositions with an overlapping domain of convergence that should give you the same function. So now let's forget that we were looking at the 4-point function. Let's just erase this sign and look only at this sign. Now you see the a fun thing, because if you just gave me a random set of deltas and L's and lambdas, as someone asked me in the break, would someone gives me like delta 1 and someone gives me this random set, would it define a consistent conformal field theory? Well, the answer is at the level of 2-point functions, you may not see anything go wrong. But here, at the level of 4-point functions, you see that these deltas and these lambdas, they must obey some very complicated set of constraints. Because for every point where that is in the common domain of convergence of these two sums, these lambdas and deltas must be such that they give you the same function, the same number. And so this, we write this as, we call this crossing symmetry. Where am I? There. So crossing symmetry schematically we want to write it like this. We just denote this complicated conformal block with some 2, 3p, lambda 1, 4p, with some symbol. Then this is a constraint on the OPE data, delta k, lk, and the lambda ijk. In fact, you have infinitely many constraints because for every position in this overlapping domain of convergence, you must get the same answer. So I have an infinity of constraints, and you have a double infinity of constraints, because of course I can pick these 4 operators, whatever I want it to be. If you're a mathematician, you would say this is associativity of the operator algebra. You fuse, it's saying that fusing 1, 2 with 3 is the same as fusing 1 with 2, 3. So this would be a mathematician's version of it. And you probe this simple associativity condition with operator 4. That's what you're testing the associativity condition with. And the reason I'm saying that is that if you have solved crossing symmetry for all 4-point functions, all positions and all 4 combinations of 4 operators, then you have tested this as a basic associativity condition in any possible way, and then you're done. So you can ask, well, what about 5-point functions? Do they give me new constraints? In principle, they don't. Someone here is working on 5-point functions because sometimes the constraints are packaged nicely in 5-point functions. In principle, knowing all the 4-point functions is sufficient. Or sorry, having crossing symmetry for all the 4-point functions is sufficient. Then you're done. Then you have a consistent conformal field theory at the level of local operators in higher dimensions. There's also modular invariance, which is a specific thing for 2 dimensions, but let's not go in there. So this is the main set of equations. These constraints mean that not everything goes. So I said the bootstrap program is to get constraints on the observables in conformal field theory. Remember that these deltas were in particular interesting because they're related to the scaling behavior near criticality. And so these are the guys that we want to know. And this is some very complicated set of constraints that involve the guys that we want to know. So can we somehow use these equations to say something about the deltas? Yep. Okay, yeah?
You say that we are looking at the property of ds intersection with dt. Can we continue by continuity is constraint on all space, or is it too much to ask for?
All space, because this 4-point function is a function of, I wrote it for identical operators, but I said, I wrote, I'll explain this in a second in more detail, but we're gonna need this anyway. So I wrote UV because I can always write all of space means just the prefactor is simple. So all of space just means all the possible values of V that can reach in Euclidean signature, and that means all the possible associated values of Z and Z bar. And I just told you that all of Euclidean space is for any point in Euclidean space. You can put the 4 points in this configuration. So all of Euclidean space is captured in the end in just this complex C-plane. And you see ds and dt, their union captures everything. So yes, any Euclidean point, you're good. More interesting is perhaps what happens if you go to Lorentzian signature. If you do weak rotation, you make these X's complex. You hit light cone singularities. Now you go through a light cone singularity. You avoid it by giving a small imaginary part to your Lorentzian time. And you go through around the light cone singularity, what kind of convergence properties do you have there? And that is interesting, and you can see whether things converge there. You can actually learn something from that. We'll get there in a second, or tomorrow.
Depending on the number of primary fields that you have in your theory, are these equations
There are always infinitely many of these primaries in the theory. I'll show that in a second. There are not always infinitely many Virasoro primaries, but there are always infinitely many primaries in my definition. So yeah, if you give me infinite data, but that doesn't fit on my laptop. So we cannot solve it. We don't have many explicit solutions of crossing symmetry. Like very simple cases, free theories and so on. But we don't know any solution exactly. Okay? Okay, so what I wanted to write is a title, because we're moving into the next section. So we're going to analyze these equations, but of course we'd like to know what these conformal blocks are. And we'll restrict ourselves to the simplest case of identical operators. And in sticking with the convention in the literature, I'm going to call the operator whose 4-point function we consider, I'm going to call it phi. Phi is not a free field from 2 lectures ago, it's just an operator. It has a scaling dimension that is whatever it is, and I call it delta phi. This is just to offload my possible confusion to you guys. So you should not be confused by this, but this is also how I generally write things in terms of this delta phi. So phi is just an abstract, one of these operators. Everything I called O now, it's now called phi. The block decomposition. Blocks, they're these complicated functions of four positions, but in fact they have the same form already as the form of the 4-point function, because they're sort of, I mean, hand wave argument is that they're built from conformally covariant gadgets, and they're made out of 4 points, and so this is the only structure you can get. But as it happens, you can also just compute them and check it. The blocks themselves have a very nice form. They just do this, x1, 2 to the 2 delta phi, x3, 4 to the 2 delta phi. And then we have lambda phi k squared sum over all k primaries, of course. And these blocks, so I told you they depend on delta 1, delta 2, delta 4, delta k, and lk, but as it happens, scalars, this function of the cross ratio only depends on delta and L. So this is the decomposition. And now it's already a bit more manageable, right? We had a function of 4 positions and 6 quantum numbers. And now I'm telling you, well, up to this free vector, it's a function of 2 quantum numbers and cross ratios. So this is more like humanly possible. Of course, it is also equal to, let's see if I want to write this out. Yes, why not? Of course, we can also swap 1 and 3 again. So swapping 1 and 3 means swapping, did I write it? Z and 1 minus Z is what I want to say. So lambda phi k squared g delta k. Okay. X 2, 3 to delta phi. So this is crossing symmetry at the level of cross ratios. So should I show you this? Like u is z bar is x12 squared, x3 4 squared, x13 squared, x2 4 squared. V is 1 minus z bar, and it is whatever it is. And here you can see that swapping 1 and 3 will give you z swapped with 1 minus z. Alternatively, of course, up there, we said that swapping 1 and 3 is swapping z with 1 minus z because it swaps this distance with that distance. So either way, swapping 1 and 3 is swapping z with 1 minus z in this. So you see, this I can move to the other side. And then I basically see that this is just x2, x3, 4 over x2, 3, 1, 4. That's basically u over v, or z over 1 minus z, times over 1 minus z, raised to the power delta phi. So if you forgive me for rewriting an equation that I already wrote, I can do it like this. There's an equal sign, so now I'm going to write it like this. Z bar over 1 minus z bar to the power delta phi. So this is crossing symmetry where I eliminated the prefactor. Well, I eliminated, I rewrote it in terms of this cross ratios. So now it's even simpler. There's no more prefactor. Everything is just a function of two positions. Maybe we should, because it's nice. So the identity conformal block, well, it should be the identity operator, which is 5, 5, 5, 5. So it's x1, 2 to the 2 delta, x3, 4 to the 2 delta. So the block should just be 1, because that gives me the right contribution of the identity. So let me factor out the identity and move it to the other side. So we'll just say that this is equal minus 1 for the identity from this guy. And then there's also an identity from that guy. So that should be plus z bar over 1 minus z to the delta. So this is our, well, people call it a sum rule, because you somehow have to get a bunch of these functions, and then you have to get this function. And the magic here is that if these OPE coefficients are real, which they check the square of, so you have some linear combination of these kind of functions labeled by delta and L, a linear combination with positive coefficients that should function. The fact that this is possible, well, this is a very non-trivial fact, and this is where sort of which is at the basis of the numerical bootstrap. So now it's just mathematics, right? You can give this to a mathematician and say, solve it. I factored out the identity. K primary, not identity. So now it's correct. Yeah. Sorry. Okay. Like I said, so this, I mean, this you can give to a mathematician. It's a mathematical problem now. So we came a long way, and now we're just in the world of almost mathematics. But the mathematician is, of course, going to ask you, well, what are these functions? And these functions are complicated, and so we should say a few words about these functions. So we'll say some properties of conformal blocks. So one property is that you should have control of these blocks, because then you just get one or two terms in the operator product expansion. So the OPE limit for these blocks in the S channel, so for G delta L, Z bar, is just Z to 0. Their things should be simple. And in fact, they are. Let me just say that, write it as follows. G delta K LK Z bar, as Z goes to 0, behaves like a very simple power. I mean, you have to work a little bit, but you have to sort of get the leading behavior of this complicated infinite order differential operator. You keep the first term of that, and then you keep the short distance singularity of the 3-point function, and then you're going to find the short distance behavior of the 3-point function, and you're going to find this. And it's just set to the delta k. Well, that's for scalars. For vectors, you get something, a Legendre polynomial in d dimensions. So where where cos theta is just the argument of z. So this is the behavior, and then you get, in fact, so this is the dimension of the primary, and then you get an infinite series of from all the descendants. But of course, they have the same dimension, the dimension of the primary plus an integer. So what happens here is that you get some integer series. So let me just write sum n equals 1 to infinity z to the n, and then some function of theta, which is just some finite sum of Legendre polynomials again with some coefficients. Oh, this also depends on delta k. Okay. But the point I want to make is that this is an integer power series. Okay. We can also do something else. We can just say, well, this is a function of two variables, and I'm just going to take z and z bar to be completely independent of each other. I can just let go of the idea that z bar should be the complex conjugate of z. This is equivalent to making these x's a bit complex, going into Lorentzian signature, for example. If you do that, then the u's and v's take some strange values. You can go into Lorentzian signature, and x12 squared can become negative, for example. Then u and v can become negative, and v can maybe also become negative or stay positive. And you're going to find solutions to z and z bar, to this quadratic equation where z and z bar are not necessarily complex conjugates. If u is, in particular, if u is complex and or v is complex, then z and z bar are not complex conjugates. One possible thing you can do is, one possible way you can, configuration you can find is where z and z bar are both real and independent of each other. I still call it z bar, but it's just another real number. And that limit is particularly useful. We'll use it soon. Let me see where I am. I'm here. So let me look at the limit. Where I send only z to 0. It's kind of an OP limit. In fact, you can check that it's kind of a light cone limit, but z bar fixed. So what you'll find there is that it's z to the delta minus L over 2 times a function that I'm going to call k delta plus L over 2 z bar plus, again, order z. So I'm writing this not just because I think these functions are nice, but actually because we're going to use this later on. And so what is k? It is it's just a 2f1 hypergeometric function. Well, what's a 2f1 hypergeometric function? That is just an infinite power series in terms of Pochhammer symbols. And what are Pochhammer symbols? Well, they are just ratios of gamma functions. And what are gamma functions? Well, that you can ask your little sister. So I'll stop here now. So this is just a light cone expansion. So that's already a fairly complicated beast, but this is about as simple as these books get. So these hypergeometric functions in particular pop up all over the place. Always in this form of this case. So you have Mathematica installed. Mathematica has a nice function that's called hypergeometric 2f1, and it computes this. It takes 4 arguments in this order, and it computes exactly this series. So the series has a radius of convergence of 1. It converges in the unit disk, but the function is extended, is analytic beyond it. So I can take, in fact, this function. Well, there's a branch cut here from the simple prefactor, but up until but this function is just the 2f1 is analytic everywhere. It has the series has a radius of convergence of 1, but there's only a singularity between 1 and infinity. There's a branch cut here, and it's analytic outside of it. So this, of course, should remind you of this domain ds, right? We're going to decompose the correlation function in terms of these k's. I'll give you another expression where these k's are more prominent soon. So we decompose the correlation function in terms of these k's. Then it should converge in this domain ds. So these k's behaved in the same domain. Otherwise, it would be a strange way to write the decomposition. And the k's indeed are well behaved in basically ds. What more should I say? There's so much more to say, and there's so little time. Where are we? See. Let me give you some explicit blocks. So nice blocks in d equals 4. So this is beautiful work. Sorry, other questions? Am I still good? Did I mess something up? I think it's correct. Whatever. No? Yeah. In d equals 4, there's beautiful work by Dolan and Osborne from maybe the very late 90s or the early 2000s, and they found the blocks. It's not that simple. And this, historically speaking, so I'm going to talk about the numerical bootstrap and how it allows us to determine the three-dimensional easing critical exponents. But historically, the first numerical bootstrap studies were done in 4 dimensions for some phenomenological reasons. And that work, there were some numerical experiments done, in particular by Slava Rychkov and his collaborators. And these numerical experiments would not have been possible if it weren't for the fact that Dolan and Osborne had actually written down some explicit form, some simple form of these blocks that you could do in Mathematica. So it was really essential that these blocks in 4 dimensions were known and had this very simple form. So Hugh Osborne is one of the honorary members of the bootstrap community because in the 2000s, when nobody cared about blocks, he was already doing this with his student Francis. So this is what the blocks look like in 4D. 2 variables depends on delta and L, that's it. So that's pretty clean. D equals 2. Even cleaner, but I'm going to write this let me write it like this. So just 2K functions. Of course, remember that in D equals 2, I'm not looking at the Virasoro symmetry. This is just a subset of the Virasoro symmetry. The Virasoro symmetry is bigger. And so if you have Virasoro symmetry, you in particular have my little symmetry with 6 generators. I talked about this at the discussion yesterday. I have 6 generators, and those are captured by these blocks. So a Virasoro block has a decomposition into generally infinitely many of what I call conformal blocks. Yeah.
say that you have Virasol generators. So does this relationship also apply to any of these blocks?
Which relationship?
When you're writing on the board, are they general to any to the board as a whole, or only the subsets you are mentioning?
If you have Virasol, you have more. So my decomposition will still work, but because you have my symmetry, you have the small symmetry, and then therefore my decomposition works. Now, the fact that you have more just means that you can write your 4-point function into a sum of Virasoro blocks, and they're big blocks. So let me write a big G. And each Virasoro blocks has an infinite sum into my small decomposition. So in particular, it does have a decomposition in my blocks. Because nothing I said is wrong in the equals to, it's just not the most efficient way to package your 4-point function. Sorry, I'm going to erase this. And then d equals 3. That's interesting, but it's complicated. So there are formulas for this. There's a differential equation, that the second order differential equation that these blocks have to solve. There are integral formulas. One funny trick you can do is to decompose a 3-dimensional conformal block into 2-dimensional conformal blocks, which works because the 2-dimensional conformal algebra is a subalgebra of the 3-dimensional conformal algebra. And so you can write it as an infinite sum of 2D blocks. That's one particular way. But then you have to compute the coefficients for which there are recursion relations and so on. Nowadays, there's good computer code for this, right? This is a function that is nice and it's just implemented in Mathematica as hypergeometric 2 of 1. This is a more complicated function. It's not directly implemented in Mathematica, but of course we have developed lots of code for it. So it's not that much more complicated than the 2D and 4D. Yes? Sorry? Well, the dumb way is to take this infinite order differential operator and act with it on a 3-point function, right? That'll work. It'll give you a couple coefficients. More interestingly, are these better ways to solve them are these differential equations that they have to obey, which I don't want to get into. So maybe you can ask me after or at the discussion session. And then you'll have some series expansion like this, where the coefficients can sort of be determined recursively. And you get a recursion relation for the coefficients, and then you're done. Sorry, you need? Yeah. We want to analyze these equations numerically in particular. Do I?
The objective of the method is to determine the delta and the L, or is it to determine the lambda?
Also, the lambdas would be nice. Yeah, everything is great. So everything is awesome.
I mean, when you ask about all these functions given, you want to go for that spatial theory, the delta, the L, and the lambda?
Well, the deltas are definitely easily measurable in experiments, the leading deltas. And the subleading are harder. The lambdas are, in principle, I think you can try to measure some of them, but of course, it becomes more and more difficult. But if you just give me the deltas, you're not going to be. The deltas would be the most interesting, but you're not going to solve this with just deltas, right? With a combined problem. But just the deltas from the lambdas, you have to know both. So I need to wrap up, but so let me just squeeze in some constraints. 2 more constraints, and then we'll do applications next. So one is What about 1-2 crossing? Right, we just did 1 and 3, but I can also swap 1 and 2. There's one more independent generator of the permutation group of these 4 elements. And I can take it to be 1, 2. Well, what happens is that, let me just stick to identical operators again. You see that the prefactor does not change, and if you do the math, you'll find z goes to z over 1 minus z, and the same for z bar. And these blocks, as it happens, do nice things. They get a simple prefactor. So if you want to check it with these things, it's important to realize that L is an integer. And you have to take into account properly the modulus and so on. But you get a minus 1 to the L. And so you get the same, but it's a crossing equation. So the correlation function should be invariant. So what we get is we get this decomposition, right? What we get is that if I sum it all up, I get the 4-point functions. And this is an equation that must be obeyed. And so you see that all the odd spins get a minus signs, but the even spins are good. And so in the OPE, so we conclude, you can work a little bit harder and conclude it rigorously, that even spins must all be 0. So in the OPE of identical scalars, primaries, only even spins. And that is the entirety of 2 crossing for the 4-point function of identical scalars. That's it. That's all you're going to get from this particular crossing equation. So there's one hugely interesting crossing equation, which is the one written here, and there's one quite boring crossing equation, which you've just solved immediately. It's like if you know a little bit about scattering amplitudes, then you know that there are only even spin partial waves in the scattering amplitude for identical scattering for identical particles. In fact, it doesn't have to be elastic. As long as 1 and 2 are the same, it's good. 3 and 4 can even be different, but you're only going to get even spins. Mm-hmm.
I don't understand why this transformation exchange 1 and 2.
1, 2, so the top here does not change, but the bottom changes. So I think it sends u to u over v and v to 1 over v. And if you rewrite this, I think. And I think if you rewrite this in terms of z and z bar, well, here it's obvious that z bar goes to z over 1 minus z bar over 1 minus z bar. And here you'll see that for 1 minus z it also works out, I think.
Because z is equal to 1, you go to infinity. 3 is going to v.
Yeah, because 1, 2 and swapping 1, 2 and 3, 4 both at the same time doesn't do anything. So it's the same as swapping 3 and 4 here. But z is the operator at position 2, right? Swap 1 and 2. That's like bringing 2 to infinity. So it makes sense. And then the last boring ingredient. So I'll end with some boring stuff, and we'll do more applications later in the next lecture. So what about these? Are they in any way constrained? Well, by cluster decomposition, we said decomposition. We want the deltas to be positive. But in fact, there's in a reflection positive theory. So so this is one. And a second. In a reflection positive theory, we want delta greater than d over 2 minus 1, d over 2, d minus 2 over 2 for scalars. And we want delta to be greater than L plus d minus 2 for technically traceless symmetric spin L operators. And if you have a representation that an operator that transforms in a weird representation of the rotation algebra, then you get some weirder bound. But these are the bounds that you get for a reflection positive theory.
Can I be semi-integer?
L, yeah, well, this is for scalar blocks, where for blocks where the external operator is a scalar, and then I'm not going to get spinners. So then L is always integer. If you're going to work with spinners, then you have to dress up everything with indices, and it becomes a big mess. It's been done. It's possible, and then of course you can work with spinners. And then you get some extra minus sign depending on the fermionic nature of things. 5 minutes. That's generous. I was not counting on that much. So these are the unitarity bounds. Let me give you a quick proof. What's reflection positivity in a theory? Well, sketch of proof. So reflection positivity or unitarity, we call it with some abuse of language unitarity, although the two are related, is the fact that if you take some configuration of points, of some configuration of excitations, so let's take 3 operators, and then I take the reflected configuration, then this correlation function is non-negative. So this is reflection positivity for us. And that extends to vector operators. So if I have an operator with the vector index, I can make it point in this way, then the other operator should point in that way. Or if I have another vector, I can also do it like this, right? So you can kind of think of this as the path integral on this half space generates some states, and this generates a conjugate state, and then you have an inner product on a Hilbert space defined on this slice that is positive. Yeah, because it's Euclidean empty space. Yeah. You can extend this to even cylinder or compact space times. Yeah. Yeah, it's this 5 to the 4 theory that we started with, Wilson, and the Ising model on the lattice is, I think even on the lattice, it's reflection positive. You can show this. So it's there are tons of examples. So if you start with the lattice, it's a bit of work. If you start with quantum field theory, it's what high energy physicists would just call unitary quantum field theory. And then we rotate it to Euclidean signature.
Usually scalars are like zero operators, so that means that between the two pairs relationship, we have one which is stronger than the other one.
Yeah, for scalars there's a different, but this does not work for spin L0. Sorry, yeah. And so this bound for scalars is actually fairly nicely shown, because for scalars, we'll just say this. So let's build a reflection positive configuration. Well, OX, O0 is definitely, it's 1 over x to the 2 delta. And this is, of course, reflection symmetric on the slice that's halfway between the two operators, any slice that's halfway between the two operators. So good, we have a reflection positive configuration, and lo and behold, so we're good because 1 is bigger than 0. So reflection positivity. Now let's do this. Act with the Laplacian on this thing. Simple exercise. Show you that this is 4 delta times delta plus 1 minus d over 2 over x 2 delta plus 1. So we're looking at one descendant and the primary. So this is in no way needs to be positive because it's not a reflection positive configuration. But of course I can act with two boxes, or alternatively I can act with the Laplacian here and act with the Laplacian there. By translation invariance I just can move the derivatives around, right? And then I get 4 delta, and then I act again with the Laplacian, so I just get the same factor but with delta shifted by 1 unit. Delta plus 2 minus d over 2. 1 over x squared delta plus 2. And this is a configuration, so it needs to be positive. And so from that you can see that there is some complicated polynomial inequality, but in particular here you see this factor is sort of the lowest. If you take, it depends a bit on the dimension. You can do, right, take the first derivative and work a little bit harder, but you see that the positivity of this thing directly comes from this factor. And there's no way you can squeeze anything below this bound, that, except of course when delta is 0, you have the identity operator. There's nothing else. This is the unitarity bound. And you see that if it's saturated the bound, if delta is exactly d over 2 minus 1, then box on the operator is 0. But that's a free scalar, right? Box on a free scalar, free massless scalar is 0. And the same you can here, for example, for spin. This unitarity bound comes from, say, let's do spin 2, then delta must be bigger than d. But what if delta is d? I have a spin 2 operator of dimension d, which is this distress tensor, and there is a descendant which is 0. So that's just conservation. So things that sit at the boundary of these so-called unitarity bounds are kind of special cases because there's some derivative that vanishes. So with this, we can start analyzing. These are all the ingredients that I need. I erased the crossing equation, but that's of course the most important equation that we'll analyze on Friday. So thanks.